Okay, the recording started. So, good morning, everybody. Welcome back to Math 115. How's everybody doing today? We surviving out there? How are things at USC? Are you on the struggle bus? Okay, Alex is on the struggle bus. Otherwise, seems like things are all right. I'm definitely on the struggle bus. I'm very underslept right now. So apologies in advance if I make any arithmetic errors. That tends to happen when I get very, very tired. But I got my coffee with me, so we're gonna make it through. We're all gonna make it through. All right. So first of all, don't forget you have an exam coming up on Monday. This Thursday is gonna be a review session. Why don't I just write this stuff down? Exam on Monday. That's March 8th. And Thursday is a review session, or a review day, I guess. So today we'll finish up doing more exponential stuff and more logarithmic stuff, and then tomorrow, I haven't quite decided what I want to do tomorrow because the next section, which I'm technically supposed to cover, is like a bunch of hogwash, and I'm not really interested in teaching it. And I don't think it's really that relevant for you guys to learn, to be honest. So I'd rather spend time on something else. So we'll either move forward, or maybe we'll dig in a little bit deeper on one of the topics we've already covered. So that'll be tomorrow. And then the exam will cover everything up to tomorrow's lecture. So that'll be everything up to March 3rd. Okay, so the material that we've covered this week so far, so like yesterday, today, and tomorrow, will be on the exam. Now, your homework assignment for the material which we covered this week won't be due until Friday of next week. But it might be good for you guys to look at it over the weekend and take a crack at some of those problems just to practice. But I like to give the week-long window. So that's just kind of how the cookie crumbles with that homework assignment right before the exam. Winds up being due after. So that's kind of my recommendation, would be to try those homework problems before the exam if you can. I'm going to post a practice exam. The practice exam is either going to go up today or tomorrow, depending on some other factors in my academic life. But then I'll post the practice exam, and I'll give you guys like a day or so to try it out, and then I'll post a video solution guide for that on the YouTube channel. That it's not mandatory for you to watch it, but it would probably be helpful. And as usual, the practice exam is not really meant to be like the end-all be-all of your studying. It's just meant to give you an idea of what is like the format of the exam, what is the general length of the exam, and how do I ask questions. It's not meant to tell you which questions I will ask. Okay, so I will take a random sampling of stuff from what we've covered, which is fairly broad, and then the exam will cover another random sampling. Some of it may overlap, some of it may not overlap. Okay, so that's about the exam. Any questions about exam stuff or homework or anything of that nature? All right, seems like not. So let's review what we were talking about last time. So last time we kind of finished up the problem that I had not gotten to at the end of Friday or the end of Thursday's lecture. Okay, so we did this half-life problem where we kind of manipulate this exponential equation to figure out what the rate is, and then we manipulated it further to figure out what the half-life time was going to be. Okay, so that was one example of a time that we use these exponential equations and these logarithmic equations in real life. And people actually do this sort of thing. When they have like a radioactive substance, they want to know how is it decaying. Okay, and then we kind of moved forward to solving exponential and logarithmic equations. Okay, and we had two main ways of dealing with the exponential equations. And today we're going to talk about the logarithmic equations. So the exponential equations, the two ways which we had were by trying to either match the powers, okay, in which case we try to write both sides as a power of the same number. Okay, so in that sense, it's kind of useful to recognize some of these perfect cubes and perfect fourth power things for that purpose. So generally, we just, if one of the sides is already a prime number, we can try to sort of divide it out from the other side until we get something which looks like a power. And if that process doesn't work, then we can move on to the log process. Okay, but usually, well, I shouldn't say usually, but a lot of the time we wind up with something like this where we have 25 to the x equals 125, and the kind of crux of this problem is to recognize that 25 and 125 are both powers of 5. And once we express both sides as a power of the same base, then we can just equate the exponents. Okay. So that was how we used the matching. And then we had some cases where matching didn't work. Okay, and the cases where matching doesn't work are when these two numbers, 5 and 3, are, should I use that word? Okay, so no, I'm not going to use that word. Are basically, if they're both prime, then you can definitely know that one of them cannot be expressed as a power of the other one. Okay, that's just a fact of life, because if that were to be true, then the number wouldn't be prime. Okay, so prime numbers are going to be sort of unmatchable, but they don't necessarily have to be prime numbers. They just have to be numbers with the different prime factorization. So for example, if we had something like, I don't know, how about 12 to the x equals 25 to the x minus 2. Okay, this is another situation where these numbers aren't prime, okay, but they don't share a common factor, and they can't be expressed as a power of another integer. Okay, 12, there's no integer a such that I could write 12 equals a to the power y, where a and y are integers. Okay, so the issue here is sort of the fact that 12 can't be written as a power of some other number, and 25 can't be written as a power of 12. So we wind up with a situation where both sides are sort of incompatible. Okay, and if we have an incompatible sides, what we do is we just apply the natural log to both sides. And that allows us to use the power rule to bring those powers down, and we get x times ln of 12 equals x minus 2 times ln of 25. And then we just kind of distribute that out and solve this equation for x, okay? It's not too tricky. Why don't we just go through it? We'd get x ln 12 on this side, and on the right-hand side, we would distribute that number ln 25 onto both x and minus 2. So we get ln 25x minus 2 ln 25. And then we would just subtract the x ln of 25x over to the other side. So we get ln of 12x minus ln of 25x equals negative 2 ln of 25. And then we can anti-distribute, rewrite the right-hand or the left-hand side as ln of 12 minus ln of 25, quantity times x equals negative 2 ln of 25. And then we just divide out from both sides. Man, should have given myself a lot more space to do this. Then we just divide out on both sides, and we get x equals negative 2 ln of 25. And we divide that by ln of 12 minus ln of 25. Okay, so this is how we use the ln method when the powers can't really be matched. And the ln method always works. So, if you just want to never learn the power method, then go ahead and just use the ln method every single time. It won't fail you. It just might not be the most elegant way to solve the problem, and it might not be the fastest way to solve the problem. So we generally reserve it for the cases when we can't use an easier method. Oh, question here that I missed from Om Kumar says, will there be questions from the first exam on the second exam? I'll say this, math is comprehensive and this class is comprehensive. And so, like, for example, to do these exponential problems, you really need to have a good understanding of, where was it? Of this stuff. The fact that if we take a power to a power, we should multiply those powers, right? We get x to the a to the b should be equal to x to the a times b. This is subject matter from the first exam. But you need to know it. For the second exam. Okay, because it's going to come up. So the prerequisites will be sort of implicitly involved in the second exam. But I'm not going to explicitly test like subject material from the first exam. So the focus of the exam will be on the material between exam 1 and now. Hopefully that answers your question. Okay, so are there any questions about the ln method for solving exponential equations? All right, well, if not, we'll move on to talk about something new. Okay, so, well, I guess it's not really something new. It's just another exponential equation. So this is just another example of a really common thing you see in word problems. They always talk about either like interest or, radioactive decay or various other like exponential phenomena in real life. And one of those exponential phenomena is population growth. And you can sort of imagine why it might be exponential if you just consider the fact that, if we have, two people and then they, mate, and then we have like four people after that, and then they all mate, and then we get like, we just keep getting more and more babies as we go along because there's more and more people, and the more people that there are, the more they're reproducing, and the more people we get, and so on and so forth. It's like a positive feedback system. Okay, so that's something that can be modeled using exponential growth. And the equation for it looks basically the same as compound interest at the bank. Okay, so for compound interest, the only difference in this equation, in fact, was just that we used the letter A, and this we used the letter A. That was really the only difference. So we only just used the letter P to mean people or population, as opposed to A to mean amount of money. Okay, so the question states, okay, if P naught, so our initial population is 1 million people, and then 10 years later, our population is 10 million people. Okay, and we're given that the population follows an exponential scale, and we're supposed to find out what is the population in 20 years from the start. Okay, and basically we're interested in ultimately solving for the population when we have 20 years. Okay, so what we're going to want to do is we're going to want to take the population initially and multiply that times 1 plus r to the power 20, and that will give us what we want. Okay, and here we have that P naught is known, it's 1 million. But herein lies our issue. We don't know what r is. And so we're just going to use the one other piece of the puzzle that we have to get it. The extra info being population at t equals 10 equals 10 million, and we're going to use that to find r. Okay? And that's like 95% of these problems follow this exact model, where basically the first step is you have to figure out what r is, or if you have e to the kt, then you got to figure out what k is. Okay, it's one of those things. And that's almost always the first step. And then they ask you to either find out what is the population at a certain time, or they ask you to find out what is the time that gives you a certain population. That's how these problems always go. So the first step is to use this extra information to figure out what r is. So how could we write this information in this orange box here in terms of our equation P of t equals P naught times 1 plus r to the power t? Let's use the information from the problem to write down an equation which expresses this fact that the population when time t equals 10 is 10 million. So let's have some help from the chat. How should we write this down here? You can take a minute or so if you want to fiddle around with it a little bit, and then we'll reconvene. All right. So what are we thinking? Have we figured out a way that we can kind of package this information in terms of our equation? Yeah, essentially, we should have. You're right. Yeah, let me write it in a slightly different way at first, but I like that you wrote it that way, Kamar. So first of all, we know that P of 10 here, right, is going to be equal to 10 million is going to be equal to our initial population, which is P naught. Well, that's 1 million, times 1 plus r to the power t. Well, I already just established here that t should be 10. So I'm going to put 10 where t goes. Okay, and the distillation of this is that we can divide both sides by 1 million. So this implies that just 10 is going to be equal to 1 times 1 plus r to the power 10, which is what Omkamar wrote down. Okay, did other students in the class find the same root here or get something similar to what I've written down here? Or did we find this challenging? It's okay if we found it challenging, that means I need to explain it better. Okay, some other students had the same thing. All right. Well, I'm not seeing anything saying that this is too terribly difficult, so I'm going to keep going with the problem. Okay, so this is kind of the distillation of what that information kind of packaged for us. So now what we want to do is, like I said, first figure out what r is. So then we would have our entire equation, and then we could just plug in whatever t value we want to figure out the population at that time. So what we want to do here is solve this equation. Okay, we want to solve this equation for r. So how do we get r by itself? Well, we could rewrite the equation first as just, well, 1 times anything is just itself. So we've got the equation 1 plus r to the power 10 equals 10. So what should we do? How can we get r by itself? Okay, we got log square root of 10. Let's try log first. Okay, log 10 equals log of 1 plus r to the power 10. Then the left-hand side is log 10 of 10, which is just 1. And then the right-hand side would be 10 times log of 1 plus r. Now, where should we go from here? I think we might have written ourselves into a bit of a corner using a log. And a log would have been a great option to use if our unknown was up here in this exponent. If our unknown was up there, then we would have successfully gotten it out of the exponent, and then we could just divide out that log, and then we'd be done. But the issue is that our unknown is actually inside the exponential equation, so there's something even simpler than a log that we can use to solve this equation. It's even simpler than using an exponential. In fact, solving this equation is really kind of outside of the purview of exponentials and logarithms in general. We learned how to solve a problem like this, I think, in the first couple weeks of class. Yeah, we can just take the 10th root of both sides. We can just take the 10th root of both sides. We take the 10th root of something to the 10th power, we get just 1 plus r. We get the initial thing, right? And then we would just get square root of 10, or sorry, the 10th root of 10 is minus 1 is equal to r. Yeah, even a little bit simpler than what we've been doing so far. We can just take the 10th root of both sides, no problem. Okay, so what is r? R is going to be something like, let's use our trusty Wolfram alpha. R is something like 0.2589 ... Okay, so let's use that information to write down our entire equation. We know that P of t is going to be equal to P naught, that's 1 million, times 1 plus r is going to be 1.2589 ... to the power t. Then if we want to find out what is P of 20, all we have to do is take this equation, which, since we found this r in here, the only unknown is just that t. So if we figure out what that t is, we can figure out what the population is. So we just do 1 million times 1.2589 ... to the 20, which is going to be approximately equal to let's see here, times 1 million. And we get what is this? Basically, this is like 100. This is like 1 million times 100, something close to 100. So we get something like 100 million people. Okay. So that's how we can use this this equation. Okay, so just to recap, our goal was to find out ultimately what is the population 20 years after we start. We used information about where we started and where we were after a certain amount of time to figure out what the rate of growth was. And once we knew what the rate of growth was, we had everything in our equation known except for the value t. So when we plugged in a given value of t, we got a specific answer, and that answer was 100 million people. Okay, so first we start with 1 million people, then 10 years later we have 10 million people, and then 10 years later than that we have 100 million people. Okay, so the rate of growth is going up. There's more people means more people reproducing, and more reproducing means more babies. Okay. Does this example about population growth make sense or sort of unclear? Makes sense. Is it a bit fuzzy for anybody? Because I can go back over it, no problem. Okay, making sense is what I'm seeing for the most part. If you want to see more examples of stuff like this, by the way, I have office hours tomorrow from 9:30 to 11:30 or by appointment. So hit me up via email. Okay, we're going to move on now and talk a bit about solving logarithmic equations. Okay, so before we talked about how to solve equations, which look like, okay, we have like some power on one side and we have some other like business on the other side. And we talked about how we solve equations like that, okay? And the reason I call this an exponential equation is that each side, okay, is an exponential expression, okay? An expression is exponential when the independent variable x is in the exponent. Okay, so the reason that this is called an exponential equation is because both sides are exponential expressions. And now we're going to have logarithmic equations, which are going to be described by equations involving logarithms on both sides. Okay. All right, so how do we solve logarithmic equations? Well, the main goal basically is to isolate the logarithm. Okay, so I'll say isolate the log, then see if you can maybe switch to an exponential equation or well, step 2 really depends. Let me put that. But sometimes we will use exponentials to undo logs. Sometimes we'll do other stuff, which maybe we'll talk about later. Okay, so let's start with this first equation. We've got 4 plus 3 times log 2 of x is equal to 1. Okay, and I am going to try to isolate this here in the following way. I'm just going to move 4 over to the other side, so I'll subtract 4. We'll get 3 log 2 of x is equal to negative 3. Then we'll divide both sides by 3. We'll get log 2 of x is equal to negative 1. Okay, so now I'm done with step 1. I've isolated the log. I just have log 2 of x on one side. And what I'm going to do at this point is basically I'm going to take both sides to be the exponent on 2. Okay, so I'm going to rewrite. If I have two things that are equal, then it will also be true if I take 2 to these things, it will also be equal, right? If I have the same power on both sides, then these will be equal. Okay, and this is what I mean when I say that I'm going to use exponentials to undo logs. because here's where the undoing is going to happen. This 2 to the log 2 of x. We learned that 2 to the x and log 2 of x are inverse functions. So when I do 2 to the log 2 of x, I just get back x. And that'll be equal to 2 to the negative 1, which is just 1/2. So that's how I do this logarithmic equation. I just have to isolate the log, and then I use the fact that 2 to the x and log 2 of x are inverses to get that x outside of the log. Okay. So let's see another example. So in this other example, it's a little bit well, maybe it's a little bit, what's the word, intimidating at first, because all of a sudden now we're working with 2 logs. Okay, we've got 2 logs, and we're supposed to isolate the log. Well, what we're going to do here is we're actually going to write as a single log, if possible. Oops. No, I always hit that button when I mean to make this thing go away. Write as a single log, if possible. So here we've got log 2 of something, and we're adding log 2 of x minus 4. So there's a log rule which I can apply here. I can write this as a logarithm with a single argument. And then that'll be equal to 1. And my question is, what should go on the inside here of this log 2? What should we write inside to combine the 2 logarithms which we're adding here? Not quite. That's a very common answer, though. Yeah, I think Mitchell's got it, but let's see what the rule was. Let's remind ourselves what the rule was. The rule was log of m times n is equal to log of m plus log of n. So in this case, we're starting with log of m plus log of n. And to write them as a single log, we should write the single log, and inside, we should take these 2 arguments and multiply them. Okay, that's really the crux of this log rule here. So what should go inside here should be what we get when we multiply x minus 3 times x minus 4. Okay. So these log rules are kind of confusing that way, where they start with something that we're adding, or maybe start with something that we're multiplying and we change it to adding or multiplying. You just have to remember that these things kind of go in this funky type of way, and you always want to write as if they have just been added on the inside, but you got to remember that we want to multiply these guys. And this equation is looking kind of watermelon-like with the color scheme. Okay, so I think if we multiply that out, we'd probably get whatever Mitchell said. So we get, what, x squared minus 7x plus 12. Yep, that's the one. Is equal to 1. Okay, so now how should I proceed? My goal here is to solve for x. I have a quadratic equation involving x inside of a logarithm is equal to some number. Move it to the left side. You mean the 1? X squared plus 7x plus 12. You mean move this outside of the log, like that? Not quite. I think you're on the right track, though. I mean, you're kind of like, well, I have a quadratic equation. I kind of ultimately want to wind up solving like a quadratic and factoring or using the quadratic formula. So I think you kind of have the idea of where you want to go, and the trouble is we just have to get ourselves there. And I'd challenge you to kind of ask yourself, what is the thing about this equation that's making it hard, right? We would have no problem solving this equation if there wasn't a log here, right? If we just had x squared minus 7x plus 12 is equal to 1, we'd be all set, right? We could just solve it like a quadratic equation. So anytime that we have an equation like this where we're like, God, I really wish that log wasn't there, let's get rid of it. So how do we undo a log? Yeah, we use an exponent. Yeah, turn it into an exponent. So which exponential function should I use to undo log 2 of something? Yeah, I should use the exponential function 2 to the x. So I'm going to plug both sides into f of x equals 2 to the x. Then on the left-hand side, I will have 2 to the power log 2 of x squared minus 7x plus 12. And on the right-hand side, I will have 2 to the 1, which is just 2. And now this left-hand side, 2 to the log 2 of something, those guys undo one another, right? So I just get left with x squared minus 7x plus 12 is equal to 2. And now I'm at the point where I think Mitchell was kind of trying to get to. Now we've gotten rid of that log and we've just got a quadratic equation and we can solve it in the usual way. We'll move the 2 over and we'll have x squared minus 7x plus 10 is equal to 0. And we'll factor then. We want a number which multiplies to positive 10 and adds to negative 7. We want minus 5 and minus 2. And that means that x minus 5 should be equal to 0, and therefore x is equal to 5. And x minus 2 should be equal to 0, and therefore x is equal to 2. So our answer is that the two numbers which make this equation, log 2 of x minus 3 plus log 2 of x minus 4 is equal to 1, true, are if we plug in the numbers x equals 5 or x equals 2, this equation is going to be true. Because all we've done this whole way is just rearrange that equation. Okay, we haven't done anything new. We've just done things to the left-hand side and the right-hand side simultaneously, which we know preserves the equality throughout. Okay, so what was the crucial step? Well, there were two crucial steps. First was to combine everything as a single log and isolate it. And the second crucial step was to recognize once we got, let me use a different highlighting color. Let me use green. Once we got here and we had an equation involving a single log and it was isolated, we wanted to figure out how we solve that for x. And if we just take a second to look at this and challenge ourselves to understand, why is this so hard to solve? It's hard to solve because the gosh darn thing we want to get it's inside a logarithm. So we get rid of the logarithm. Okay, the whole point here is this log is really messing us up, so let's get rid of it. Use your mathematical principles to turn a problem which is hard to understand into a problem which is easy to understand, or easier to understand at least. Okay, are there any questions about how we solve these logarithmic equations? Okay, I'm getting the sense that maybe we should try one more example of these log equations. So we'll do that. Let me just see if I can find a good one for us. Let's try this one. Log 2 of x plus 4 equals log 2 of x plus 3 plus 1. Okay, so our goal here is to find out what x is. Or rather, which values of x will cause this equation to be true. Okay. So we're just going to follow these steps, okay? We're going to isolate the log and write it as a single log if possible. And we're going to use exponentials to undo the log. Okay, so I think the first thing that we should probably do is get both of the logs on the same side. We'd have log 2 of x plus 4 minus log 2 of x plus 3 is equal to 1. And I want to write this left-hand side as a single log. And this time, rather than adding, I'm subtracting these two logs. So what should my single log look like? What should go inside these parentheses here? Yeah, Kamar's got it. Does everyone see that connection here? This is coming from the log rule we had, which said that log of m divided by n is equal to log of m minus log of n. And this time we're kind of being asked to go in the opposite direction. We have two things being subtracted, two logs being subtracted. we combine them into a single log by taking those arguments and dividing them. Okay. So inside we should have x plus 4 divided by x plus 3. Okay, now what should I do? Not the log of both sides. You've already got a log on one side. My goal here is to get rid of a log. Yeah, we want to get the log by itself, but it's already by itself, right? We've just got one log on one side and a number on another side. So the log is totally by itself, and we've written it as a single log. So we can rewrite it, that's right. Yeah, we should use the exponential function now. That's right. I think Justin's got the right idea here. Yeah, we should plug both sides into the function 2 to the x. On the left-hand side, we get 2 to the log 2 of x plus 4 over x plus 3. And on the right-hand side, we have 2 to the power 1. So we get, ultimately, x plus 4 over x plus 3 is equal to 2. And from here, it's just algebra, right? We do just x plus 4 is equal to 2x plus 6. Move the x over, we'd get x here, and on the left-hand side, we'd have 4 minus 6 is negative 2. Okay, so x equals negative 2 makes this true. Now there's kind of one thing that we should still probably check, which is to make sure that x equals negative 2 is in the domain of both of these equations. But you can see if you plug in negative 2 into x plus 3, we'd get 1, and we can do logs 2 of 1, no problem. And if we were to plug in 2 for the other one, we'd get log 2 of negative 2 plus 4 would be 2. And we can do log 2 of 2, no problem as well. So we're all set. So this is going to be our solution to this problem. Okay, so the moral of the story is, first, get all the logs on one side and write them as a single logarithm. Then get rid of the logarithm by plugging both sides into the appropriate exponential function. And that's how we got rid of the log, because we wanted to solve for something which was inside of a log. So we plug both sides into 2 to the x. The 2 and the log 2 of x cancel. And we're left with just x plus 4 over x plus 3 is equal to 2, at which point that's just a rational equation. We know how to solve rational equations. We learned that kind of towards the beginning of the class. All right, any lingering questions about logarithmic equations? I'm getting the sense that you guys find this to be one of the more challenging topics we've talked about. Is that a solid assessment? Looked difficult, but was easy to pick up on. Always hated logs in general. Yeah. Yeah, logs are annoying, I think, because it can be really hard to have like a really intuitive understanding of what a logarithm even is. Okay, and I think that can provide a lot of students trouble who up until now have been kind of used to having like a really intuitive understanding of what's going on. But sometimes in math, we run into these concepts which we don't really understand, but we need to understand. I mean, we need to have the knowledge of how to manipulate them mathematically. So rather than hoping for a great understanding of logs at this point in your mathematical career, what you can search for instead is try to get a good understanding of the log rules. Okay, the really important ones are that a to the log a of x is equal to x. Log a of a to the x is equal to x. Log of x times y is equal to log of x plus y, log of y. And log of x over y is equal to log of x minus log of y. Log of x to the power p is equal to p times log of x. Okay. Are there any other ones? I guess the sixth one would be that log a of x equals y if and only if log base argument, so x equals a to the y. So these are basically the 6 facts about logs, which you need to understand. And I think that if you focus really hard on understanding what it really means to do log a of something, I think you're gonna run into a roadblock of not being able to form a really nice intuitive understanding of what is going on there. But rather, what I would recommend you to do is focus on understanding how to apply these rules. Okay? So when you have an equation involving a logarithm, you can always come back to this page and see which one of these rules could I apply to achieve the outcome that I want. And if I have an equation, the outcome might be different depending on what I'm trying to solve for. Okay, so if I have something like log a of x equals 17, and I'm trying to get x, well, I know I want x to be outside of the exponent, or of the logarithm. So I look for equations which take something which is inside a log and put it outside of a log. And that leads me to equation number 1, right? I want to get x by itself. And here's an equation where x is by itself. So I try to see, is there a way I can apply this to this equation here to get that thing out of there? And the answer is, yeah, if the left-hand side, instead of log a of x, if the left-hand side looked more like a to the log a of x, and then the right-hand side also looked like a to the 17, then this left-hand side would be exactly what my rule number 1 is, and that's just equal to x. And then I'd get x is equal to a to the 17. So this is the game that we should play with logarithms, is rather than trying to have a great understanding of what a logarithm does, which might be a little bit tricky for pre-calculus students to, or even calculus students and beyond, to really understand what they're doing, we should try to understand them through these rules. I think that's the best spiel that I can give on, or that's my best advice maybe that I can give on how to handle logarithms at this point. So doing lots of equations, doing lots of practice problems in which you use these 6 rules to manipulate logarithmic and exponential equations. Once you get used to these rules, you will start to see the numbers in the matrix like Neo, and you'll just see, when you see one of these problems, you'll know just what to do. Okay, any questions before we move on to some word problems? All right, seems like not. So basically what I have left for us for the rest of the day is just, you know, a bunch of word problems, because these log and exponential equations oftentimes are coupled in these word problems. So let's do some examples. So the first example is this problem here, and what does it say? It says that we should find the time required for an investment of $10,000 to grow to $18,000 at an annual rate of 6% compounded yearly or compounded continuously. So this is almost like a doubling time problem, except we're not trying to quite double our investment. We're trying to get it to grow from 10K to 18K. Okay, so let's remind ourselves of what the equations are corresponding to interest compounded annually and interest compounded continuously. So the equation for the yearly interest is going to be A of t is equal to A naught times 1 plus r to the power t. And for continuous interest, we instead have A of t is equal to A naught times e to the kt. Okay? And in general, these two are going to give us similar results, but not exactly the same. Okay, so we're gonna see how long it takes for our investment to double, or not double, to grow from 10K to 18K in each case, and we'll compare and contrast and see which one has is our investment growing quicker with. Okay, so we actually know that our annual interest rate is 6%. Okay, so that's telling us what? R, let's do A first. So R is going to be 0.06. Okay, we also know what A naught is. That's our initial investment. That's going to be $10,000. And A of t, our ending investment, is going to be $18,000. And then the final piece of this puzzle is just t. And that's our question mark. That's what we want to know. So let's fill in the pieces of this equation. A of t goes on the left-hand side, so we get 18,000 is equal to 10,000, that's my A naught, times 1 plus r is 1.06 to the power t. Now I want to get t by itself. And the trouble is, t is in the exponent. So are there any tools that we've learned how to use recently that can allow us to get t out of the exponent? Suppose first of all we can divide by 10,000. We'll have 1.8 equals 1.06 to the power t. How about that? Give you that one for free. But now how should I get t out of this exponent here? Yeah, log, right? So I can apply the log to both sides. I could use the common log, or I could use the natural log. I like using the natural. Oops, that's the wrong page. Is that the wrong page? No, that's the right page. I like using the natural log, so that's what I'm going to use. We'll do ln of 1.8 equals ln of 1.06 to the power t. Now, how does that help us? What can I then say about the right-hand side? How can I rewrite this right-hand side? Yeah, I can use the power rule. Remember, that's the most important rule we learned about logs. We get t times ln of 1.06. And now to get t by itself, all I have to do is divide both sides by ln of 1.06. And I get t is equal to ln of 1.8 divided by ln of 1.06. And let's see what we get when we do that. Wolfram on my PC real quick. We do ln of 1.8 divided by ln of 1.06. And we get approximately 10.09 years. And that's it. Okay, so we start with this information, and this was even kind of a nice problem, in which case they gave us really all of the information except for the one thing that we want. And we didn't even have to solve for the rate, they gave us the rate. So all we had to do was plug into our equation and manipulate it in order to solve for t. Since t was initially in an exponent, we used a logarithm and the power rule to get it out of the exponent. And then we just had some number is equal to t times some number. And the way we solve for t in that situation is just by dividing out the coefficient, ln of 1.06, and we get this expression here, which we can then go ahead and type into our calculator, and it will tell us exactly what that is. Okay, we just do ln of 1.8 divided by ln of 1.06. And by the way, you can do this using log if you want. If you want to do log 10, So that's fine. You just replace all these by log 10. And it doesn't even matter that we use a different log, because guess what? At the end, we have a quotient of logs. And when we're doing the same type of log on the top and bottom, these will proportionally be the same. You'll get different numbers on the top and bottom, but they will be the same. They'll have the same proportion. Okay, so you can do that if you want. But I kind of like using ln because I have to write one less letter. And I'm lazy. Pro tip, all mathematicians are lazy. That's not true, but this one is. Okay, any questions about how we solved part A? Okay, I'm going to go through part B really quickly before we close for the day. So in this case, we've got the same kind of stuff. We've got A of t is still going to be 18,000. A naught is still going to be 10,000. Our k this time is going to be our rate, which is 0.06. And t is again our question mark. So we're interested in solving the equation 18,000 is equal to 10,000 times e to the 0.06t. So again, we start the same way by just, first we write it as 1.8 is equal to e to the 0.06t. And then again, the thing I want is up here in this exponent. So what do? I apply natural log. Except this time it's even easier. We don't even have to use the power rule. We can just use the fact that ln and e to the x are inverses to automatically get 0.06t on this side. And we just divide both sides by 0.06. And we get approximately 9.80 years. Okay, just another standard rearrangement of an exponential equation to get what we want. So all in all, we see that the continuous interest, our investment grew a little bit faster. Okay, but still pretty close. All right, well, I think we'll stop there for today. So tomorrow we'll see a little bit more examples about this. And I'll have office hours as well. So that's it for today. Everybody have a great day. If you have any questions, feel free to say after and type them out in the chat or speak up on your mic. Yep, thanks, Heidi, you too.